And finally, the third and the most difficult problem is an object is being thrown from a certain height at certain angle. So it's a combination of the previous ones. Let's say the certain height will be known to us, such as, for example, 30 meters. And let's say initial velocity is 25 meters per second. And the angle will be 50 degrees. I will set my coordinate system again as previously, 0 on the ground, x to the right, and y high up, pointing up. So we will need the equation that has the initial height involved. But even before that, as usual, let's break down the initial velocity onto v initial x and v initial y. We did it last time, so we should be getting more and more comfortable with this idea. I'm sorry. Can't write cos twice. So for initial velocity on the x, it's cos. For initial velocity on the y, it's sin. So we have v initial at 25 cos 50. Looks like it is 16 meters per second. And here, 25 sin 50 at 19 point something meters per second. Simplifying it, simplifying. Questions of interests. Obviously, time of flight. Naturally, range, the distance how far the object fell. There's also one more interesting question, which is called final velocity or velocity at landing. Why this question is different? Why did I not ask before? So before, I could have asked velocity at landing, and interestingly enough, it will be the same magnitude, but just different direction. So for a second, I'll borrow a different color, and I will point it roughly like that. So this final velocity will also be 9.4 meters per second. It's just pointing down somewhat at an angle. So these two vectors are equal in magnitude. In here, though, initial velocity is much greater than, I apologize, final velocity is much greater than initial. And we might be interested in figuring out its value as well as maybe its angle. I don't know which one, maybe this one. I'll color the angle for now. So we will need the angle for sure. Let's set our two equations. As usual, x is vix multiplied by time. Y is initial y, which is initial height. VIY multiplied by time minus 9.8 times squared divided by 2. What do we have from here? We have the same concept. At landing, y coordinate is 0, because I decided that my 0 is on the ground. So initially it's 30, it goes up, down, at landing it's 0. At landing, y equals 0. So what do I have for my second equation? 30 plus 19t. Where's 19 coming from? From here. Minus, instead of 9.8 divided by 2, I'll just allow myself 4.9t squared. What is this? It is pure quadratic equation. There are methods how to solve it, and we usually know that we will result in two roots. One of them most likely will be negative. Clearly, if we kind of imagine parabola on this side, we are in the negative zone already. Our interest is a positive root, which after calculation is approximately 5.1. If you have a question how to calculate t from here, come see me. We'll just solve a quadratic equation, or I'll show you how to use Wolfram Alpha or Desmos for it. So our time of flight is already known. Range follows the same pattern as before. Is first equation. We have 16 multiplied by time. You know what I just realized? That I usually put numbers here, and this time I did not. Not sure what I was trying to achieve. Even instead of y0, I can already put numbers. Now that's much better. That is the equation. Those are the equations that describe this particular case. So let's see, 16 multiplied by 5.1, and we calculate. It looks like we gain 82 meters. As always, put that on pause and consider if it's in fact correct or not. Something along those lines. That's kind of good. Now, the velocity at the end. It's a complicated question because velocity at landing. We haven't really spoken about much about velocity, but what we know is that it can be broken down into components, and we have in fact seen that when we had our interactive demonstration when there was cannonball firing. I insisted that you observe the horizontal component, which was not changing. Whatever horizontal component I had initially, which is 16, it will actually stay as 16 throughout the whole travel time. Vertical component, however, yes, that one is changing. And the formula for that would be V initial y minus gt. V initial y. Where's this formula coming from? Remember, there's a definition of acceleration. Change of velocity over time. Final minus initial divided by time. So from here it's coming. Just specifically applied to y component. Our initial was 19 minus 9.8 multiplied, and our time was 5.1. And yes, when we calculate that, we will receive a negative number. Please, no panic. The only thing it's telling us is that initial vertical is pointing in a different direction than the final vertical. Initial vertical is pointing up, then the ball goes up, then the ball goes down, and then the final vertical component is pointing down. So clearly they have a different sign. One is plus, one is minus. The sign at this point, however, is irrelevant. Why? Because when we calculate the actual v, we will be doing squares as per Pythagorean theorem. I apologize, I don't need to put the little initial, just Vx and Vy, and the square root out of that. So it will be 16 squared, 30 squared. Notice how I completely disregard the negative sign. None of my interest. When negative is squared, it will be positive, so no need to overload the drawings and the solutions. That will be 34 meters per second. And at this point, we feel like, oh wow, we have solved a lot, but not yet. We haven't found the angle. Remember that green piece that I highlighted? We need that angle, which is here. Not very accurate. Let's try again. So that angle, let's call it theta, can be found using tangent function. Tangent is this side divided by this side, which is y component divided by x component, which is 30 over 16. And so what happens that theta is tangent minus 1 of this ratio, which is equal to 62 degrees. Last reminder, in this question, we did not have directions commonly used previously, such as south, north, east, west. So we cannot really write that this is pointing south so many degrees east, etc., etc. We have to say where the theta is located. So 60 degrees between Vx and V. Or we can say down to the right. Or the safest method is just to include this drawing. If this drawing is included, then actually it's quite clear where the theta is. It's marked on the drawing. So that's it. We found the time, the range, and the final velocity, including its magnitude and direction. You may think that that is everything. However, there's one thing that we didn't discuss yet, is actually the maximum height of the ball. And I'll probably create a separate video for that, because I haven't even spoken about it in class.